The sun has been burning for 4.6 billion years. It will burn for another 5 billion. On any human time scale, that's permanent. That's forever. You'd be forgiven for thinking stars just exist, reliable, eternal, fixed. They're not. Every second, the sun converts 600 million tons of hydrogen into helium, and in that process, it loses 4 million tons as pure energy. 4 million tons per second. Gone. The sun is lighter right now than it was when you started reading this sentence. It has a fuel tank. The tank is draining. What happens when it empties? That's the question, and the answer isn't what you'd expect, because stars don't all die the same way. Some go quietly, some detonate. Some leave behind objects so extreme that physics itself starts to stutter. The difference between a quiet death and the most violent event in the universe comes down to one thing: how heavy the star was to begin with. A star is a stalemate. That's the simplest, honest way to put it. At the core, gravity is trying to collapse the star inward. It's always trying. Gravity doesn't take a break. But fusion is pushing back. Hydrogen nuclei slamming together at 15 million degrees, releasing energy, creating an outward pressure that keeps the star inflated. This balance holds for millions, sometimes billions of years. But it's not permanent. It can't be, because fusion consumes fuel. The hydrogen runs out, the helium builds up, the fuel composition changes, and when it does, the stalemate tips. This is the thing that most people miss about stellar death. It's not a sudden event triggered by some external force. It's the inevitable conclusion of a tug-of-war that began the moment the star formed. Gravity was always going to win eventually. The question is just how long fusion could hold it off, and how violent the final surrender would be. Mass is what determines that. Take a star like the Sun, medium-sized, unremarkable by cosmic standards. When the hydrogen in the core runs out, fusion there stops. But fusion continues in a shell surrounding the core. The core itself contracts. It has no pressure source anymore, so gravity squeezes it. As it contracts, it heats up. That heat floods into the surrounding layers and causes them to expand dramatically. The Sun will eventually swell to perhaps 200 times its current size. Mercury gets swallowed. Venus probably gets swallowed. Earth, maybe. The models aren't fully settled, and it doesn't matter much because life on Earth ends long before the expansion gets that far. But the point is, the star gets bigger as it dies. It inflates while its core collapses. Those two things happen simultaneously. Eventually, the core gets hot enough to start fusing helium. Carbon and oxygen form. The star stabilizes briefly. Then the helium runs out. And here the Sun hits a wall, a fundamental limit set by its own mass. It's not heavy enough, not hot enough to fuse carbon. It can't take the next step up the fusion ladder. So the outer layers drift off, slowly, beautifully if you're watching from a safe distance. They form what astronomers call a planetary nebula, glowing shells of expelled gas lit by the hot core left behind. Some of the most stunning images from Hubble are planetary nebulae: the Ring Nebula, the Cat's Eye, the Helix. Each one is a grave marker and a spectacle. What's left at the center is a white dwarf, the compressed core, roughly the size of Earth, but with more than half the Sun's original mass packed into it. No fusion, no heat source, just a glowing ember, slowly cooling over trillions of years. Eventually it becomes a black dwarf, a cold, dark rock. No such black dwarf exists yet. The universe isn't old enough. The coolest white dwarfs we've found are still thousands of degrees. That's the quiet death, the long exhale. Now increase the mass significantly. Stars more than about 8 times the mass of the Sun don't stop at helium. They don't stop at carbon. They're heavy enough, hot enough to keep pushing up the periodic table. Neon, oxygen, silicon, one fusion stage after another, each reaction building heavier nuclei from the ash of the previous one. And each stage burns faster than the last. Hydrogen burning takes millions of years. Helium burning takes hundreds of thousands. Carbon burning, a few thousand years. Oxygen, months. Silicon, about a week. 1 week. That's how long it takes to fuse the silicon core into iron. Then everything changes. Iron is the trap. Every fusion reaction up to iron releases energy. That's why it can sustain the outward pressure against gravity. But fusing iron doesn't release energy, it absorbs it. Iron sits at the bottom of the nuclear binding energy curve. It's the most tightly bound nucleus. You can't get energy out of it by fusing it into something heavier. You'd have to put energy in. The star has been running a 10 million year long energy release. And now the engine demands payment instead. The iron core grows. It's held up by electron degeneracy pressure, a quantum mechanical effect where electrons resist being squeezed into the same state. It's nothing to do with heat, nothing to do with fusion. It's pure quantum mechanics holding up billions of tons of iron. But that has a limit, the Chandrasekhar limit, about 1.4 times the mass of the Sun. When the iron core exceeds it, and in a massive star it will, electron degeneracy pressure fails. Not gradually, catastrophically. The core collapses. In roughly half a second, a sphere of iron the size of Earth compresses down to a sphere about 20 kilometers across. The density becomes extraordinary, comparable to the density of an atomic nucleus, but stretched across a city-sized object. Protons and electrons are forced together. They merge into neutrons. A flood of neutrinos is produced. The collapsing core suddenly hits a new resistance, neutron degeneracy pressure. The core goes rigid, almost instantly. The outer layers of the star, which have been falling inward at a quarter of the speed of light, smash into this rigid surface and bounce. A shockwave tears outward through the star. This is the supernova. The energy released in that half second, just the collapse of the core, exceeds what the Sun will produce across its entire 10 billion year life by a factor of 100. The visible explosion, the thing that outshines entire galaxies for weeks, is just the shockwave reaching the surface, a side effect, an afterthought, energetically speaking. The real power is invisible. 99% of the energy from a core collapse supernova is released as neutrinos, not light, not heat, neutrinos. Neutrinos barely interact with anything. They pass through the entire Earth as if it isn't there. A light year of lead would stop about half of them. They are the universe's most antisocial particle. And yet, in February 1987, a star in the Large Magellanic Cloud, 168,000 light-years away, exploded. Supernova 1987A. The neutrino burst from that explosion passed through Earth. Detectors in Japan, the United States, and the Soviet Union caught a total of 24 neutrinos over 13 seconds. From an explosion 168,000 light-years away. The number that actually passed through Earth was somewhere around 10 to the power of 58, roughly 10 billion, trillion, 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 trillion. The detectors caught 24, and that was enough to confirm the entire theoretical framework of core collapse. Here's the detail that still gets me. The neutrino burst arrived at Earth about 3 hours before the light did. Because the neutrinos are produced at the core and pass through the star almost unimpeded. The shockwave that produces the optical display takes hours to travel from the core to the star's surface. The neutrinos left first, traveled 168,000 light years, and still arrived ahead of the light we could see. 1987A is the only time in history we've detected neutrinos from a source outside the solar system. It's a one-time confirmation of a theory physicists had built over decades. The universe gave us one data point. It matched. What's left after the explosion depends on how much mass is in the core when the dust settles. If the remnant core is between about 1.4 and 3 solar masses, neutron degeneracy pressure holds it up. What you have is a neutron star, city-sized, incredibly dense, spinning fast. A teaspoon of neutron star material would weigh about 1 billion tons. The surface gravity is roughly 200 billion times Earth's, and newly formed neutron stars can spin hundreds of times per second, conserving the angular momentum of their enormous progenitor compressed into something 20 kilometers wide. The way a figure skater pulls their arms in and speeds up, except instead of a skater, it's a dead star. Some neutron stars emit beams of radiation from their magnetic poles. When those poles don't align with the rotation axis, the beam sweeps around like a lighthouse. If Earth happens to be in the path of that sweep, we detect a pulse, regular, precise, sometimes more accurate than atomic clocks. These are pulsars. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell. The signal was so regular that for a brief, serious moment, it was considered as a possible artificial transmission. They called it LGM-1, Little Green Men. It wasn't, of course. It was something stranger, a dead star spinning 30 times a second, beaming radiation across the galaxy. Now, if the remnant core exceeds roughly 3 solar masses, neutron degeneracy pressure fails too. Nothing holds it. No known force, no quantum mechanical effect, nothing. Gravity wins completely and permanently. The core collapses to a black hole, a point, or near enough, where the density becomes infinite by the equations we have, and where the equations themselves stop making clean predictions. The event horizon forms, the boundary where escape velocity equals the speed of light. Inside it, everything that falls in moves toward the center, not because it's attracted to it in the gravitational sense, but because in the geometry of space-time inside a black hole, all future-pointing paths lead inward. Space itself is falling. We don't know what's at the center. The equations say a singularity, infinite density, zero volume. But most physicists think that's the math telling us we've hit the edge of our theory, not a description of actual reality. Quantum gravity should fix it. We don't have quantum gravity yet. Here's the part that reaches backward in time to you personally. Everything heavier than iron in the universe was made in supernovae and neutron star mergers. Not gradually, not slowly, in seconds. During the explosion, the shockwave blasts through layers of material. The conditions, extreme temperatures, extreme neutron flux, drive a process called rapid neutron capture, the R process. Nuclei absorb neutrons faster than they can decay, building up heavy elements in a runaway chain: gold, platinum, uranium, iodine, lead. Hundreds of isotopes created in the seconds of an explosion that's been dead for billions of years. The calcium in your skeleton was forged in a star's core. The iron in your blood, the stuff that makes hemoglobin red and functional, came from a supernova. The oxygen in your lungs right now, the carbon your DNA is built from, stellar fusion products, scattered by stellar deaths, condensed into a solar system, then into you. In 2017, LIGO detected gravitational waves from two neutron stars spiraling into each other and merging, a kilonova. Telescopes around the world watched the optical afterglow. Spectroscopic analysis confirmed it. The merger produced gold. Strontium. Heavy elements synthesized in the collision of two city-sized objects moving at a significant fraction of the speed of light. You are not just made of stardust. That's too gentle a phrase. You're made of supernova shrapnel and neutron star wreckage, scattered across billions of years and reassembled improbably into something that can sit here and think about it. The mechanism is still not fully understood. I want to be honest about that. The shockwave from a core collapse supernova should stall. The simulations show it losing energy as it fights through the infalling outer layers of the star, the very layers that are still collapsing inward even as the shockwave tries to move out. Without something to revive it, the shockwave dies, and the whole star collapses silently to a black hole with no visible explosion. Something revives it. The best current answer is neutrinos. That immense neutrino flood, even though neutrinos barely interact with anything, deposits a tiny fraction of its energy back into the stalled shockwave. Enough to restart it. Enough to blow the star apart. But a tiny fraction of an enormous number is still a significant number. And the details of how exactly this energy deposition works, the convection, the instabilities, the geometry of the shock, are still being actively worked out in three-dimensional simulations that require some of the most powerful supercomputers on Earth. The broad picture is right, the details are hard. They also don't know exactly where the mass threshold is between neutron star and black hole formation. We suspect some massive stars collapse directly to black holes without a visible supernova. They just disappear. There's one candidate, a massive star in the galaxy NGC 6946, designated N6946BH1, that simply vanished from view around 2009. No explosion detected. A star and then no star. If that's what it looks like when a star collapses directly to a black hole, we'd probably miss most of them. Gravitational wave astronomy is changing this fast. Every neutron star merger LIGO detects is a data point on the equation of state of ultra-dense matter. Every supernova detected in neutrinos, if another 1987A happens close enough, will probe the collapse mechanism directly. The data is coming, the understanding is following, imperfectly and excitingly behind. There's something worth saying plainly before we're done. The death of a star is the condition for your existence. Not in a vague poetic sense, literally, mechanically. If no star had ever died, the universe would contain hydrogen and helium and nothing else. No carbon, no oxygen, no nitrogen, no phosphorus. No organic chemistry. No planets with crusts of heavy elements. No you, no biology, no wondering. The violence wasn't incidental. It wasn't a flaw in the design. It was the mechanism. The supernova is how the universe distributes the products of stellar fusion across space, how it seeds nebulae with the material for new star systems, new planets, new chemistry. The star doesn't die into nothing, it dies into everything that comes next. Dirac said once that a physical law must have mathematical beauty. What I find beautiful here isn't the equation, though the equations are beautiful, it's the chain. The hydrogen cloud collapses into a star. The star fuses hydrogen into heavier elements over millions of years. The star dies and scatters those elements across light years of space. A new cloud collapses, seeded with that material. A rocky planet forms. 4 billion years later, something on that planet builds a detector, catches 24 neutrinos from a dying star 168,000 light-years away, and confirms a theory about how stars die. The star dies, the knowledge survives, the material survives. You're the material. You're also the knowledge. Both things, at the same time, made of the same atoms that were forged in stellar cores and scattered by stellar deaths before the Earth existed. Whatever broke apart in that explosion, it became, eventually, something that could understand what happened to it. That's not poetry. That's just what the physics produces, given enough time. And it's stranger and more worth thinking about than anything I could dress it up to be.